Hi Math, I'm Andy. Today we're given three different curves on a graph, and we're told that one of these curves represents the function, one of them represents the derivative of the function, and one of them represents the second derivative of the function. And so just by looking at these graphs and examining the slope of the tangent lines, we're going to be able to figure out which one is which. Now, in order to do this, I'm just going to choose an x coordinate on this graph, and let's examine the slope of the tangent line. So I think let's just start with the y-axis. And so here we have that spot where x is equal to 0. And in this spot, let's look at the slopes of the tangent lines of each of these curves. And I'll just start by making an assumption, and then we'll kind of work from there. So let's just guess, and let's say that this curve here, let's pretend that this is the function. So here, I could say if this is the function, then the function at 0 is about negative 1.5. That's what that point kind of appears to be. I'm just estimating. Now the slope of the tangent line, to me at this point, seems to be pretty horizontal, pretty flat. So I could say that the slope at this point is 0. So what this would mean that if this curve was the function, then the derivative of this curve at that x value, because the derivative represents the value of the slope, I should get 0, because that's what my slope is. And so we're saying, remember, this is the same x that we're plugging in, and we're now getting out the value of the slope of the original function. So what I'm looking for is I'm looking for a 0, 0 on my graph. And it turns out that this graph goes through the origin. And so this potentially could be the derivative of this, just right now. So let's look for that second derivative. We would do the same thing. Let's draw the tangent line at this slope. The tangent line definitely looks negative. It almost looks like it's 1 over 1, pretty close, but it's hard to tell exactly. And so what we're saying is, it's almost like let's assume this derivative is now just a function. 0, 0 is a point on that function. So if I were to take the derivative and I were to plug in that x value of 0, the slope that I'm getting out looks like negative 1. And I'm just going to put negative 1-ish because it's hard to tell negative 1-ish. So the next graph, the second derivative, should go through the point 0, negative 1, but it doesn't. This curve goes through 0, 6. So that's going to be a problem. And so I can't assume that this is the function because the only thing that would follow would this to be the derivative, but then this is not the second derivative. So we kind of need to re-look at this. Let's take another assumption. And just kind of going on this idea that this middle graph here goes through the origin, and I see that up here the horizontal tangent line has that 0 slope. So let's kind of start there, and this time let's assume that this is the function. We'll call this guy f of x. So that tangent line has a slope of 0. So the first thing we'll start off just kind of with your idea is if x is equal to 0, it looks like y is equal to 6. And that's just a point on the function. It doesn't really have any significance here. We're just kind of looking at how the math notation works. So if I were to take the derivative of f and I plug in a 0, what I should get is the value of the slope at this point. And so my slope is 0. So that checks out. I can see, is there a graph that goes through 0, 0? Yes, there is. And so this potentially could be the derivative if this is the function. So then let's look at that derivative. This is now kind of like the point of the derivative. And if I take the second derivative, which is essentially the slope of this graph, when x is equal to 0, I should get that negative 1-ish that we were talking about earlier, because the second derivative at 0 is negative 1-ish. So I look at this third graph and I notice that this third graph here goes through the point 0, negative 1.5-ish. And so that seems to check out pretty good too. So I am under the assumption here that this curve will make it maybe the yellow curve. Let's call this one the function. Let's use orange to represent this curve. We'll call this one the derivative. And we'll use this green to make the last one. And we'll call this one the second derivative. Now I just want to maybe check another point just to really make sense of this. So I'll slide over and maybe let's just check this x equals negative 5 point. Maybe this might help. So over here we said that the original function we think is the yellow highlighted kind of big wave. We think the derivative is the orange kind of smaller wave, and then we think the green is the even smaller amplitude of the wave. And so let's check this point at negative 5, and let's just see if it kind of follows our same assumption. So my first function goes through when x is equal to negative 5, the y value looks like it's about negative 4.8-ish, and it doesn't really matter. The function is just at some point, but what we want to investigate is the slope of the tangent line at this point. So we'll draw that slope of the tangent line. Looks maybe like this, and I see that it's a positive number. It's some positive number. And so I'm going to say that the derivative when x is negative 5 is some positive slope. So this means that when I plug in negative 5 into the derivative function, I should get some positive number. So I look up here, and at x equals negative 5, I have two positive numbers. So we thought that this orange was the derivative, and so this kind of matches. Let's say that this slope is positive 2. It looks like it goes up 2 over 1, kind of, doesn't it? Up 2 over 1. This slope actually could be close to 2. And so I notice in my first derivative function, that point 0, 2 exists on that function. Because remember, this derivative is the x value and the slope of the original curve's value. So it could be following what we assumed. This could be f prime of x, because when I plug in the negative 5, I get that positive 2, which was what we're just guessing is the slope of our function. So then we do the same thing. Now we're going to kind of say this orange line, which is the derivative. Let's look at the slope of the curve of that function. And I see that this tangent line also has a slope. And if I had to kind of eyeball it, looks like I go up 1 over 1, up 1 over 1, pretty close to that. And so when I look, and maybe it's even a little bigger, it doesn't quite hit up 1 over 1 perfectly. And so my second derivative, it should work out that when I plug in a negative 5 into my second derivative, I get the value of the slope from the first derivative. And we're saying this value is positive 1 and an ish, a little more than 1. And so when I look at this green function, I see that it goes through that point. It goes through the point negative 5 and then a little more than 1. And so both of these spots, when x equals 0 and when x equals negative 5, they seem to work out that the yellow function is the original, the orange function is the derivative, and the green is the other derivative. And it should work out in just about all these places. Look, the slope is 0. This point goes through 0. The slope is positive, and this point is positive. So it kind of works out in all of these spots. Here, my slope is negative, and the orange goes through a negative point. The orange tangent line slope is positive, and the green goes to a positive point. So when we're looking for this, we're looking at the slope of the tangent line at that point, and that will be the output of the derivatives function. And so hopefully that helps make sense of this.